In this lecture, we'll be covering some fluids preliminaries. Namely density, which is represented by the Greek letter rho, pressure, represented by a capital P. Now be careful in my handwriting and in your handwriting not to confuse the Greek letter rho with a capital P. Let's see, volume rate of flow. Which we'll represent by a capital letter Q. And also this concept of continuity, which sort of means conservation of volume or conservation of amount of fluid. Okay, if you've taken chemistry, a lot of these concepts will probably be familiar. And with each of them, we will try to do a sample problem. So, starting with density. Density just means the mass of a fluid per unit volume. So density is, by definition, equal to mass of a fluid divided by the volume in which that fluid is contained. Now, for many fluids, density is pretty much constant. So, for example, water, let's say rho water, is pretty much always 1 gram per cubic centimeter. cc is just a shorthand, by the way, for centimeter cubed. Now I should really make this a triple equal sign because this is a definition. So in physics we use triple equal signs to mean definition. Density is just defined as the amount of mass in a fluid, mass of a fluid contained in a certain volume. So for water and many other liquids, density is pretty much constant. For some other fluids, such as air, the density is very non-constant. You can compress air and increase its density. So what can we do with this? We could ask a sample problem. It's clear. Sample problem could be what is the mass of a 2-liter bottle of soda? And now soda is mostly water, so the density of soda is pretty much going to be 1 gram per cubic centimeter. And the volume is 2 liters. So the question is then, we need to convert either cubic centimeters to liters or liters to cubic centimeters. Now, I happen to know that 1 milliliter is a cubic centimeter. Since 1 milliliter is 1/1000th of a liter, we can convert this cubic centimeter. What we wind up with is, since the cubic centimeter is on the bottom, we wind up with 1000 grams per liter. Now recall the definition of density. It is defined as mass divided by volume. So mass is equal to density times volume, and this is equal to 1000 grams per liter times 2 liters, and that is 2000 oops, 2,000 grams, or 2 kilograms. So if you take a 2-liter bottle of soda, stick it on a scale, you should get about 2 kilograms, or 4.4 pounds. Alright, I'm going to erase, so if you're pause if you're still studying any of this. Okay, next concept was pressure. Basically, when a fluid exerts a force, a terrible job of fixing my P. Alright, looks like a P now. When a fluid exerts a force, we can define its pressure as the force exerted over some area divided by that area. And fluids do tend to exert forces distributed over some area. If you think about, say, the force that water is exerting on the inside walls of a cup, the force is distributed over that entire inside area of the cup. You think about the crushing force that water applies to a diver. It's distributed over all the diver's skin. So fluids tend to exert forces distributed over areas, and the pressure is the force divided by the area over which it's distributed. So, what can we do with this? We can do a oh, by the way, so the units of pressure, this is going to be some number of newtons, the units of force, divided by square meters, the SI unit of area. And this newtons per meter squared, there's a shorthand for this, and it's Pascal, PA for short. So, let's do a sample problem with pressure. Oops. With pressure. Suppose we have a car tire, and a car tire is filled with air at about 30 psi. And we could then ask about what is the size of the contact patch that the car tire has with the road. So let me see, let's see, car tire pressure of usually about 30 psi. And by the way, psi is just a shorthand for pounds per square inch. And we want to know what area of contact patch this car tire is going to have with the road. So let me try to explain what I mean by that with a drawing. Okay, here's a tire. And it's got some it's coming into contact with the road. This is a cutaway of the tire, so what we're looking at here is the bottom of the inside of the tire. And a certain area of that tire is in contact with the road. And the reason this happens, if you look at a car tire with pressure that's too low, sometimes what you'll see is this, or a bicycle tire. So there's the tire, and here's the road. And the point is, it's not just contacting at a point. The tire is sort of sagging, and part of it's laying flat on the road. So there's actually not just a contact point, but a whole contact patch with some area. And so we're going to calculate what that area has to be, let's say, for a car that weighs 3,000 pounds. So Basically, in order for the car tires to exert 3,000 pounds of force, that's going to be all coming from the air pressure inside the tires, because the rubber, it's pretty stiff, but compared to the weight of a car, it's not really much. So the contact patch area has to be, recall that, pressure equals force divided by area. So the contact patch area is the force divided by the pressure. The force in this case is 3,000 pounds. The pressure is 30 pounds per square inch, and let me go ahead and write that as pounds per inch squared. Make it a little bit more clear that the pounds cancel. Let's see, so this is 1,000 divided by 10, or 100. The inches squared comes up to the top, and did I do that right? 3,000 over 30 is 1,000 over 10, which is 100. So 100 square inches is the total contact patch. And that means that for each tire, if this is a car with 4 wheels, so this is the area of the total contact patch. And so if this is for four wheels, the area is then just 25 square inches. Per wheel. Okay. Onward. I'm going to erase this, so pause it if you're still studying it. Next concept, volume rate of flow. This is probably the most difficult one we're doing in this lecture. And volume rate of flow is defined as the amount of volume flowing through some pipe, like a garden hose, sewer pipe, a straw, anything like that, per second. So we'll call that delta T. Volume divided by time. Volume per unit time. That's the volume rate of flow. Now, if we consider for a moment a pipe, garden hose, something like that. Let's say it's a circular pipe. So there's some cross-sectional area A of this circular pipe, and there's some fluid flowing through it with velocity. Let's consider this cylindrical volume of fluid that I'm drawing here. And it's going to have some distance, some length. Let's call this delta x, just for a moment. And it's moving at some velocity, which is, of course, equal to delta x over delta t. And the volume of this cylindrical volume of fluid is equal to the cross-sectional area of it times this length, delta x. So I'm going to write that a little bit more neatly for you, delta x. Area times delta x. So, if we want to now calculate the volume rate of flow, I'm going to take this definition of velocity, rearrange it to write delta t equals delta x over v. Thank goodness for the undo button. And we're going to substitute in this expression for the volume and the delta t into our definition of the volume rate of flow. Now, be careful both with my handwriting and yours to distinguish somehow between volume, which I'm writing here as a capital V, and velocity, which is a lowercase v, and my lowercase v's always have these little tails so I can tell the difference. So let's substitute these into the definition for volume rate of flow. Up top we get area times delta x, and on the bottom we get delta x over v. Delta x's cancel, v comes up to the top. So in any pipe, straw, garden hose, whatever it may be, the volume rate of flow turns out to be equal to the area of that pipe times its velocity. Let's do a sample problem. Help me undo key, thank you. Sample problem. With the volume rate of flow. Q, which we have just shown, is equal to cross-sectional area times velocity. Suppose we want to fill up a pool, a swimming pool. So that's pretty big. I'll draw it. And here we are. I'll give us some ground to stand on. Here we are. Filling up a pool. Here's our hose, our garden hose, running to the side of the pool. And I don't know how big pools are, but let's say 100,000 liters. That might be a very large pool or a very small pool. I don't fill pools very often, so I'm not sure. But let's say this pool is 100,000 liters, and there's some water coming out of this hose. It's landing at the bottom of the pool, and let's say the pool is 2 meters deep, or 6 feet deep, and the water lands on the bottom of the pool 1 meter horizontally away from the edge. And let's say our garden hose I'll draw it. Garden hoses look sort of like that. Has a diameter of 1 inch. Seems reasonable. And the question is then, how long will it take to fill the pool? You've got guests coming over. You want the pool to be ready when they get here, so you want to know how long this is going to take, whether or not it will be ready. And if not, how long they'll be waiting. So, if you want to attempt this problem by yourself, you can pause the video here and attempt it, and then come back to the video and see the solution if you want, or you can just watch and we'll go right into the solution. Okay, so going into the solution. This is a two-part problem, and that is because I haven't actually given you the velocity of the water flowing through the garden hose. Instead, you'll have to find that, and that's the first part of the problem. And once we have the velocity of the water going through the garden hose, we can determine the volume rate of flow and how long it's going to take to fill a pool of a given volume. So how are we going to find the velocity going through the garden hose? Well, I said how far the water goes into the pool, how far horizontally from the edge it goes, and how deep the pool is where the water lands. So this is essentially delta x and delta y in a projectile motion problem. So we can use projectile motion to get the velocity. So let's do that real quick. Delta x here is going to be velocity times time. Now velocity, I just wrote velocity, not velocity x or velocity y, because the garden hose is laying flat on the ground. So the velocity is going to be purely horizontal when the water exits the garden hose at the edge of the pool. And of course there's no vertical acceleration. Delta y, now there's going to be no initial vertical velocity, so delta y is just minus 1/2 gt squared. And of course it's minus 2 meters, minus because the water travels downward. So we want to determine velocity. So we can take this equation with delta x in it and solve it to get velocity equals delta x, which is known, divided by time. Time at this point is not known, but we can solve this one, and that's going to give us that time equals minus 2 delta y. Again, the minus sign is okay because delta y is negative, divided by g, and then we're going to square root all of that. So substituting that into here, putting them together, we get v equals delta x divided by square root of minus 2 delta y over g. Okay, I won't put any numbers in right now except to note that we now have the velocity. All these are knowns. And let's see. Well, actually, yes, we should put in some numbers, right? That's a useful thing to do. So we have delta x is 1 divided by square root of 2 times delta y. Delta y was minus 2. The minus sign cancels out. And then we had divided by 9.8. And that gives us a velocity of 1.5 meters per second. Get rid of the box. Okay. Yeah, that did not go well. Okay, so we've got velocity. Now we can turn to the fluid mechanics part of this question and calculate the volume rate of flow. That's going to be area times velocity. Area is pi r squared, or pi d over 2 squared, multiplied by velocity. Let me create create a line here just so my equations do not get mixed up. Pi d over 2, d is 1 inch. what? The velocity actually rounds to 1.6 meters per second. So we'll stick with that. And what we've got here is pi, which is 3.14, times d over 2 was half an inch. Now we need to convert the inch to centimeters, so that means we divide by 2.5, because there's 2.5 centimeters in an inch. Wait, no, multiply by 2.5. That gets squared, and then we multiply by our velocity, which is 1.6. Oh, wait, we converted to centimeters. But we actually want to then convert that to meters, so we divide by 100, because it's 100 centimeters in a meter. Let's see. Did I get that right? Pi d over 2, that's half an inch, times 2.5 converts that to centimeter, divide by 100, that converts it to meters, and then we square it, and velocity of 1.6 meters per second, and the volume rate of flow is 0.00079. Now, we converted everything to SI units. That means this is an SI units. SI units for volume is cubic meters per second. Okay. That's our volume rate of flow. Now, recall that volume rate of flow is, by definition, volume divided by delta time. So we can now solve for delta time as volume divided by volume rate of flow. And volume is 100,000 liters. Now, we discussed before, there is a milliliter is a cubic centimeter. So 100,000, let's do the unit conversion down here. Volume is 100,000 liters. A liter is 1,000 cubic centimeters. And cubic centimeters, let's see, 100,000 times 1,000 is a million. So I'll just call that 1 times 10 to the 6. A cubic centimeter, let's see, we need to convert, we've got centimeters. To convert to meters, we divide by 100, but we need to do that 3 times because it's cubic centimeters to cubic meters. And so that's 10 to the 2 to the minus third power, which is, well, 10 to the 2 to the minus third power. What is happening? What is happening? Oh, I did this wrong. 100,000 times 1,000 is 10 to the 5 times 10 to the 3. This is 10 to the 8th. Okay. I knew something seemed wrong because I was about to get that my pool was 1 cubic meter, and that would be like a really tiny pool. So, 10 to the 8th times 10 to the minus 6. This gives 100 cubic meters. That sounds much more reasonable. 100 cubic meters. That sounds like a pool. That's a 10 meter by 10 meter well, no, okay. No, it's not. Ignore that. We get now, we've converted this all to SI units, so we have 100 meters cubed divided by 0.0079 cubic meters per second. So the cubic meters on the top and bottom cancel, the seconds survive, and let's just put that right into Google. 100 divided by 0.00079. And that is, well, a lot of seconds. So let's divide it by 60 to turn it into minutes, divide by 60 again to turn into hours, and what are we looking at? We're looking at a lot of hours. Let's divide by 24 to get it into days, and basically we're talking 1.5 days. So, I hope your guests are not getting here until tomorrow, because it's going to take 1.5 days to fill that pool. Okay, I'm going to erase, so if you're still studying this, pause now. Okay, finally, we're going to talk about continuity. It's just a concept. It's essentially conservation of volume. So what it says is that, if we have some pipe, maybe it starts out larger diameter and then turns smaller diameter. Continuity just says that whatever volume goes in, that same volume comes out. So that means also we can just divide both sides by delta T. That means the volume rate of flow on both sides has to be equal. So if this is A1 and this is A2, well, the volume rate of flow on both sides is the same. So that means that A1 V1 equals A2 V2. And so we can consider doing a problem with this. Suppose we have such a pipe and we have water coming into it at 100 that would be very fast water. Let's do 1 meter per second. That's still probably a lot of water. Let's make this be a 1 foot diameter pipe. And let's let this be a, on the other end, 1 inch diameter. All these little dots keep coming up. Oops. Keep my 1 inch. And we have fluid coming in at some velocity of 1 meter per second. That is a lot of water. The question could be then, what is the velocity of the fluid coming out the other end of the pipe? So this is V2, this is V1, and we have, just applying continuity, we have area 1, V1 equals area 2, V2. We want to solve for V2, so that's V1 area 1 divided by area 2. And because the diameter on the left side is 12 times more, because a foot is 12 inches, and the diameter on the right side, area 1 over area 2 is going to be 12 squared. And the result then is 1 meter per second times 12 squared, which is 144 meters per second. Very fast fluid coming out the other side. Okay, so this concludes some fluid preliminaries with sample problems. In the next lecture we will cover Bernoulli's equation.